Unmute. Saurabh, unmute your mic. Not audible. No. No, no. Not.
Am I audible now?
Yes, you can go.
So, before starting the session, I would like to introduce our foreign expert to the all the participants with a brief introduction to him. Uh, Today, we are having with us Professor Karu PSL, who is the distinguished professor in the electromagnetic and antenna engineering at University of Technology, Sydney. Professor Karu is the Australia's 2022 Professional Engineer of the Year and a Fellow of Royal Society of New South Wales, IEEE Engineers Australia, and a Director of Innovation for Humanities Proprietary Limited. His Metasteers team won the prestigious Australian National Eureka Prize, Australia's Oscar, for outstanding science in Australia in 2023. And he received the Primer Prize for Leadership in Innovation in the New South Wales in 2024. He has published over 750 papers and has been cited over 16,000 times, and his H index is 63. He has served as a senior editor of IEEE Access, associate editor of IEEE Transaction on Antenna and Propagation, IEEE Antenna and Propagation Magazine, IEEE Access, and the lead guest editor of the several journals, including IEEE Antenna and Wave Propagation Letter. He is a track chair of IEEE Antenna and Propagation Society, URSI, for several years and has chaired or served in many conferences, technical program committees. Thank you, everyone. Now, I request Professor Karu to start the lecture session. Sir, handing over to you. Am I audible?
Yes, yes.
Hello. Can you hear me now?
Yes, sir.
Yes,
You are
sir, you are audible.
Yeah.
Sir, unmute your mic, please.
Hello.
Now it is
Is
fine.
it good? Okay. Let me try the camera. Both of them are in one device. Oh no, the camera doesn't work. Doesn't matter. You can hear me, right?
Yes, sir, you are audible.
Okay. I will bring the mic closer to me. That way I don't have to shout and start sharing. It was working very well before when I tried the headphones. Okay, good morning, everyone again. As you know, this is the GIAN course on. Let me find my. That is fine. In course on advancing antenna technologies using metasurfaces. And so in this course, as I heard, there's a whole range of audience from undergraduate to faculty. So I don't assume a lot of prior knowledge in this field. Some of you may be experts in RF area, but some of you may not be familiar with some of the basics. So my plan is to start from the fundamentals in an area, and then go to some common types of antennas, not all of them, but few select that I learned, and some that are not very common. And after that, we focus on few areas and go deeper into leaky wave antennas, resonant cavity antennas, and near field transformation and metasteering, using metasurfaces for beam steering. So that's the plan. Let's see how it progresses, because this is a lot bigger, a lot more extensive exercise than I usually do for overseas organizations online or physical. So you already heard about me. I'm not prepare you on this slide. I have to work out how to change the slides.
Sir, you can do for slideshow, means full screen. Then it will be, I think,
Okay.
fine.
I have slides so running on the side. Says. So this is where this is coming from. I am in Sydney. This is popular part of Sydney, Opera House in the bottom, Harbour Bridge, Circular Quay, ferry terminal, cruise terminal, Hyde Park on the other side, Darling Harbour, and in the center, you can see my cursor, right? This is the central business district, and my university is somewhere in the middle here, very close to the central station. So we are basically in the city center, a very busy area. I will not go a lot about my university. This is my building, engineering building. My office is somewhere here. And we have quite a few incredibly strange looking, crazy looking buildings. One new one, a glass one, a very ugly one, and so on. These numbers are somewhat outdated now, but that can indicate that we have fairly large proportion of postgraduate students. They are very small relative to some Indian universities, as you know, but they are significant in Australian context. It's a relatively young university. We are still university is younger, under 50 years. So normally we are ranked the top university in Australia under 50, and one of the few top in the world young universities under 50. So my research area, it's all this course is based on research in electromagnetic and engineering. Our focus is to do high quality research at doctoral level, PhD or higher. That is reflected in a lot of reports we are getting, like the thesis examination reports. Normally our examiners are overseas in North America or USA. They often rate our thesis, my students' thesis, in the top in the world. We published a lot in IEEE journals, such as Transactions in International Propagation, MTT, EMC, etc. You already heard about my publications and the other awards. So all these other things are the secondary byproducts of good research. That's the way we see it. Award, citations, H index, and prizes. We work a lot with the government departments, companies, overseas universities, collaborate a lot. I can show you some of our collaborators, and we are funded very well by various organizations, industry and government organizations. We had some very exciting collaboration projects with IIT Kanpur for a long time, and some of you were associated with that. I think Chandra was associated with that doses. These are some of our recent prizes and awards, and the details of this you already heard, and you can find a lot of details in my, if you Google or if you go to my UTS website. If you just Google my name and UTS, you will get there. A lot of information are there. So I will not take more time on this, except the collaborators. As you can see, these are overseas companies, well-known companies, satellite operators, and other companies, and then whole list of Australian companies like Cochlear, Optus, Benelec, then government organizations, some overseas, and some Australian, Department of Defense, US Air Force, etc. Research organizations like CSIR, that's a Commonwealth, it's a federal research organization in Australia, DSTG, Defense Science and Technology Group, and some other research organizations overseas, such as Communication Research Center in Canada. Then a lot of universities, European, like Stuttgart University, Swansea, Politecnico, Torino, Turin Polytechnic, Loughborough in UK, etc. We have joint papers with a lot of these universities, the staff, academics in these universities, and few Asian universities. I think University of Delhi South Campus, very long collaboration with Professor Anand Verma for a long time, and recently IIT Kanpur. we had a Australia-India strategic research project for 3 years with IIT Kanpur. So we had a lot of collaboration, researchers, academics, exchanges between the two. And so when we get to the end of this course and think about collaborations, possibly, hopefully this will result in something like that. Okay, so I think one of the questions or points mentioned in the outline is what inspired us, or in the abstract. Before I get to this, I think I will do the overview of antenna. So I will switch of these slides. I have several sets of slides, and go to the antenna basics one. And on slide slow from beginning.
Are you there, sir? Hello, are you there, sir?
Hello, hello. Yeah, so every time I change the slides, it goes back to mute.
Okay.
Can you see the slides?
Slides are available. It is
Okay.
antenna
Yeah.
basics.
So remind me every time I change the. I think it goes back to mute.
Okay. Okay.
So this is this is for those who are not very have limited experience in this field. Some antenna basics and some example antenna configurations. While doing that, I will the other slides as well. So why do we need antennas? What is their purpose? So you can define in different.
You are not audible, sir. Hello. Hello. You are not audible, sir.
Hello. You can hear
Hello.
me, right?
Now. Hello.
Can you hear me now?
Now you are audible.
Yeah, it's the USB is playing up. Yeah, you're doing a good job. Yeah, alerting me. Right, every time when I goes mute, yeah, just give me a shout like that.
Okay.
I hear you very well. I can hear my speaker works. It's only the mic.
Okay.
So if you don't hear from me, I am actually troubleshooting.
Okay.
Basically, I had to disconnect and reconnect the USB. So going back to that, there are electromagnetic waves that are guided inside waveguides in transmission lines. And then there are electromagnetic waves that are freely propagating in space. So the purpose of antennas to create the second type, to make waves that are freely propagating in space. To generate those at one end, also for receiving those when we need to capture. The receiving antennas are used to pick up radiation coming from specific directions. There's a beautiful history of electromagnetics and radio waves. The discovery of radio waves by James Clerk Maxwell formed the theoretical foundation. Actually, there's more earlier than that. Maxwell put all these equations together, nicely compiled it. I had the opportunity to go to Maxwell's house in Scotland, I think last year, and they have amazing displays. The house he grew up when he was a child. So that was beautiful history. Then Hertz, we all know the Hertz, the unit for frequency. 1988 did the first demonstration of radio waves. And then Marconi, his entrepreneurship skills motivated him to apply and demonstrated wireless telegraphy, transmitting information over Atlantic Ocean in 1901. From a simple instrument like this, making a spark at one end that creates electromagnetic waves and that are picked up by a loop at the other end. So Maxwell's and the other were theoretical, but at that point, this is just an experiment that proves Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. But in fact, we can see some electromagnetic waves, right? The optical, they are also electromagnetic waves, but usually they are treated in a different way. So that brings us to the electromagnetic spectrum. That's very, very wide. We can define an electromagnetic wave based on the frequency, that's number of oscillations per second, that's in Hertz, named after Hertz, or by the wavelength. The wavelength lambda is the distance between the peaks of a wave at a given instant of time. And these two are related. Wavelength lambda is the velocity of light divided by frequency. So the radio frequency waves, which we normally do research on, are in this part of the spectrum. Frequencies around 10 to the power something, 10 to the power 4 to 10 to the power 8 maybe up to this, 10 to the power 12, and wavelengths are in the order of some 10 to the power 3 meters, 1000, 1 kilometer to 10 to the power minus 2. And when the wavelength becomes few millimeters, we call them millimeter waves. Otherwise, microwaves or radio frequency waves. Some examples, 60 hertz is the power line frequency in North America. In Australia and India, I believe it's 50 hertz. Then audio spectrum around some hertz, hundreds of hertz. AM radio is around some megahertz. FM radio is around 100 megahertz. And microwave on at 2.45 gigahertz. Then we use gigahertz, megahertz, gigahertz for communication, 3G, 4G, 5G. 5G now goes to 20 gigahertz in some countries, 40 gigahertz and so on, called millimeter wave 5G. And for satellite communication, we use a lot of frequencies from very low L band to very high frequencies like Ka band, which is around 20-30 gigahertz. So those are all wireless communication applications. Then for other electromagnetic wave applications like radar and so on, these very wide range of frequencies are used. So the waves we can see, the visible, they are also electromagnetic waves, but they are not included in this presentation. We are not working in that area. Infrared is between those two. And then very high frequency or very small wavelength waves. Okay, so how do we make radiation? What do you need to make radiation? We need charge. Okay, suppose we have a charge moving at a constant velocity that will not radiate. Electromagnetic radiation is created by accelerated or decelerated charges. And sometimes those charges are electrons. That is like, for example, time varying currents. So if you have a charge that's moving at a constant velocity, that means constant speed in the same direction, it will not radiate. But a charge that's undergoing constant acceleration will radiate. The charge undergoing momentary acceleration will radiate. A particle that goes back and forth, a charged particle that goes back and forth, has acceleration, radiates. That is a very simple way to understand whether a particular device setup would accelerate or not. For example, the DC, direct currents, do not radiate. So one way to create radiation by applying a voltage source across a wire to oscillate in time at a certain frequency. The current in a wire will vary sinusoidally with time, and the charge will experience sinusoidal acceleration. The oscillating charge, that is a charge that accelerates and decelerates, that will radiate. So we will look into that kind of antennas. The other aspect, very important for electromagnetic waves, is the polarization. There are different types of waves. The waves in free space are transverse electromagnetic waves. That means if the wave is propagating in this direction, the electric field is transverse or orthogonal to the direction of propagation. That is shown in red lines. The magnetic field is also orthogonal to the direction of propagation, and also that's blue, and also it is orthogonal to the electric field. So the three are orthogonal to each other: electric field, magnetic field, and direction of propagation at 90 degrees to each other. In electromagnetic radio frequency waves, we define the polarization as the direction of the electric field. For example, this wave has a vertical electric field, right? So it's vertically polarized. This is different in optics. In optics, the polarization is defined with respect to the magnetic field most often. So this is a linearly polarized wave because the electric field is always in the same direction, vertical direction. Then there are circularly polarized waves. In those, the electric field is not along the same direction, like here. Rather, it rotates with time in a circular fashion. Sometimes it's very easy to figure out polarization. For example, if you're using an antenna like this, we will get back to this antenna soon. It's a dipole antenna. All the currents are in a vertical direction. So it's a vertical dipole that has vertical currents that creates vertical electric field, a vertically polarized electric field. Then an antenna like this, the same dipole, now horizontal, has a horizontal electric field, creates horizontally polarized radiation. Another very important parameter, or actually it's a plot of antenna, is the antenna radiation pattern. Truly, it's a three-dimensional pattern that describes in which directions the antenna radiates. So this is an example radiation, 3D radiation pattern of an antenna that says it radiates most in the Z direction along the Z axis and less in the other directions. So it's a graphical representation of power density, watts per meter squared, radiated by the antenna in different directions. But instead of power density, you can also plot it in terms of the electric field strength, volts per meter, or you can normalize that. Then it's called normalized radiation pattern. To understand radiation pattern, because these are almost always, the 3D patterns are plotted in spherical coordinates, not Cartesian X, Y, Z, but rather spherical coordinates are theta and phi. So all antenna engineers must be very familiar with the spherical coordinate system. So R is the radial vector or radial unit vector. Theta is the angle measured between the R vector and the Z. So that's easy. Phi is the other angle that is a little bit tricky. To find phi, we make the projection of R vector on XY plane, right? So that then we get this line. We project this onto XY plane, we get this line. And then measure the angle from x-axis, starting from x-axis in the positive direction, that is towards y, So this angle is the phi. And those are the two variables, theta and phi. Then we plot the radiation as a function of theta and phi. But often we just plot this in a 2D way. So this is called 2D pattern cut. If we cut this radiation pattern of an antenna on a plane, you get a 2D figure like this, a 2D radiation pattern. That is easier to visualize, easier to plot. So typical terms you use is the main lobe, that's the direction of the main radiation. Then we have side lobes or minor lobes, the radiation going in other directions. Then the radiation null, there's no radiation in this direction and this direction, those are the nulls. The angle between those directions called beam width between first nulls. One of the very important parameters is the half power beam width, HPBW. That is, so this is the direction of maximum radiation, right? Main lobe. And half power is half of this power. Suppose we are plotting here the power density. In this case, it's normalized so that the peak power density is 1. And then in this direction, power density is 0.5. So this is a half power density direction. And this is the other corresponding half power density direction. So angle between these two is the half power beam width. Also, we normally mention power, etc. in decibels. Decibels is 10 dB of power, right? So half power is 10. So 10 times log 10 power is in decibels. Half power means 10 times log 10, 0.5, which is minus 3. So this is also called 3 dB beam width, because if you plot this pattern in decibels, 1 will be 0 in decibels, 10 times log 10, 1. 0.5 will be minus 3 approximately. 10 times log 10, 0.5 is equal to minus 3 roughly. So that is the minus 3 dB level. If you plot the pattern in rectangular plot like this, angle versus radiation, normalized, now this is in decibels, so the peak in linear scale 1 becomes 0 dB. Half power points, 0.5 becomes minus 3. So you can easily work out the half power beam width from here to here. That is more or less the same, the radiation pattern. So it's 5:30 now. Remind me, what is the plan? We take a break now and reconvene at, it's my time, 5:30, your time, I'm not sure. Is that the arrangement? I think it's good to take a, yeah, it's your lunch time, right? Noon IST. So you can take a lunch break. I can take a coffee break or something. It's 5:30 p.m. evening tea. Actually, only 15 minutes. It's only 15 minutes break, right? Okay, let's take a 15-minute break and come back in 15 minutes, 5:40 in your time, 12:15. Okay.
Okay, sir.
Okay, thank you.
At
Bye.
12:15 here. Dear participants, am I audible to all?
Yes, sir.
We will be resuming the session after 15 minutes. That is 12:15 around.
Oh, okay.
Okay.
Okay, sir.
Okay.